Okay, let's dive right into this. We rely on large language models for some seriously complex tasks these days.
Absolutely. They're uh, pretty incredible tools.
Yeah, they can code, analyze data, even tackle advanced math problems by laying out their thinking process step by step. It's incredibly powerful.
It really is. That structured thinking is key.
But you know that feeling when you ask a really simple question, something that should be instant?
Uh-huh.
And you can almost feel the AI revving up its full, elaborate reasoning engine, like it's overthinking it.
That's the problem we're talking about.
Yeah.
That step-by-step approach,
Yeah.
often called chain of thought reasoning.
Right, OT.
Yeah, go to T.
Mm.
It's what gives these models their depth on hard problems. They build a path to the solution.
But it's like using a freight train to deliver a single letter.
Exactly. It works, but it's incredibly inefficient for simple tasks.
Inefficient feels like an understatement sometimes. Applying that heavy-duty reasoning to every query means generating way more text, more tokens than necessary,
Right. More tokens, more compute, more memory.
and just takes longer. It's the AI equivalent of, making a mountain out of a molehill.
Precisely. So a major goal in current research is finding a way to get the best of both worlds.
How do you mean?
Well, maintain that powerful reasoning capability for when it's truly needed, but ditch the overhead for simple things. We need efficiency.
Which brings us to the central question driving this deep dive straight from the source material you shared.
What's that?
Can an LLM learn to decide for itself when to deploy the heavy reasoning and when to just give you the quick, direct answer?
Ah, yes.
Can it become smart enough to know when not to think so hard?
That's the core idea. And the research we're unpacking is a paper from the National University of Singapore that introduces a framework called Thinkless to do just that.
Thinkless. I love that name. It perfectly captures the goal, doesn't it?
It really does.
So our mission today is to understand how this Thinkless framework teaches an LLM to make that autonomous decision, balancing getting the right answer with doing it efficiently.
Sounds good.
Let's start by really nailing down this problem of constant thinking.
Right. So chain of thought, as we said, is transformative for tasks requiring real logical inference, multi-step deductions.
Like those math benchmarks they always use.
Exactly. Things like the math benchmarks they test these models on. Laying out the steps isn't just for show, it's often how the model arrives at the correct answer for hard problems. It's almost a necessity for complexity.
But as the paper highlights, the moment you apply that same process universally, boom, inefficiency explodes.
Yeah, for problems that could be solved directly, the model still generates all those intermediate steps.
The paper points out reasoning models can generate many times more tokens than standard models, 5, 10, even 20 times more.
That token generation translates directly into increased computation and cost.
Right. If your AI is generating pages of internal monologue for every single simple question,
Well, that adds up incredibly quickly. It makes deployments more expensive and responses slower for the user.
the motivation is clear then. We need targeted thinking, not default overthinking.
Exactly. We want smart thinking.
So researchers have definitely tried to tackle this before Thinkless. What were some of the previous approaches to making reasoning more efficient?
Well, people have looked at trying to make the reasoning process itself shorter, like generating fewer steps in the chain,
Okay.
or using different techniques just to make the output generation more efficient overall.
Okay, but that's still about making the thinking more efficient, isn't it? What about the idea of switching between thinking and not thinking?
Right, that's where hybrid reasoning comes in.
Hybrid reasoning.
Yeah, the idea of models dynamically switching modes. Can the model decide, this looks easy, I'll give a quick answer? Or, this looks hard, I need to think it through.
And how have people typically implemented that dynamic switching before this paper?
Often it's been done with manual rules or external systems
Yeah.
kind of bolted on.
Like what?
You might set a fixed budget, don't generate more than X tokens unless you're stuck. Or you explicitly signal the model with prompts like, okay, now use step-by-step reasoning. Or maybe use a separate small model to act as a router, trying to guess the problem difficulty.
Manual prompts or external routers. That feels a bit clunky, doesn't it?
It is clunky, like we're still babysitting the AI's cognitive process.
Yeah.
Precisely. And the big limitation is that these external methods, manual rules, separate routers, they rely on external knowledge. They don't fully know what's going on inside the main language model.
Ah, okay. So the model doing the actual work knows itself best.
Right. The model doing the actual problem solving knows its own capabilities and its own internal state best. An external router might guess difficulty, but the model itself has a better handle on whether it can solve this particular problem quickly or needs to, struggle through it.
And this external control often leads to suboptimal decisions, the paper says.
Yeah, because it lacks that internal context.
This raises the key question that the Thinkless paper really tackles then. How can the LLM itself learn to make this crucial decision about when to engage its deep reasoning?
That's the core innovation. They frame it as teaching the model to make an autonomous decision
Okay.
about whether to generate a short, direct response or a long, detailed reasoning response.
And how does Thinkless teach the model to make that internal decision? What's the mechanism?
They use a reinforcement learning framework. The trick is that the model learns to output one of two special control tokens as the very first thing it generates.
The very first token.
The very first token. If it predicts short, it commits to generating a concise answer. If it predicts think, it commits to generating a full reasoning chain.
Wow. Okay, so the model makes the decision upfront before it even starts generating the main content of the answer.
Exactly. It's learning a policy.
Oh.
Given this input query, what's the best first token to output to maximize my chances of getting a good reward?
And that decision, according to the paper, is influenced by what it learns about. What factors?
Well, the query's complexity, for one,
Yeah.
and also its own ability to handle it effectively in either mode. A more capable model might solve something complex quickly anyway.
And they mention the user's desired trade-off between speed and accuracy. How does that factor in?
That's built into the reward function. That's the feedback signal and reinforcement learning.
Right, the rewards.
The model learns by trying things and seeing what kind of reward it gets.
Mm-hmm.
And the reward system encourages both getting the right answer and doing it efficiently.
Why is reinforcement learning, RL, a good fit for this?
Because it's all about learning from consequences, right?
Okay.
The model tries outputting short or think, generates the rest of the response, and then gets a reward based on whether the answer was correct and how long it was.
So trial and error.
Exactly. Over time, through trial and error guided by the reward, the model learns which decision, short or think, is likely to lead to a higher reward for a given type of query. It learns to adaptively select its strategy.
Okay, let's get into the training process. It's a two-stage affair, right? Not just straight RL.
That's right. Very important. Stage 1 is called distillation for warm-up.
Distillation. Warm-up. What's the main goal there?
The purpose of this first stage is pretty fundamental. It's to make sure the base language model is capable of actually producing both kinds of responses.
You mean the detailed reasoning and the concise answers?
Both.
Yes.
When you explicitly tell it to, using those think or short tokens.
So you're basically teaching it the mechanics of generating both modes first, like how to do it, but not when to choose yet?
Exactly. They do this using supervised fine-tuning. Standard stuff, really.
How does that work?
They take example queries and get two expert models, a good reasoning model and a good instruction following model to generate responses.
Okay, two experts.
For each query, they pair a reasoning answer prefixed with think and a short answer prefixed with short. The base model is then trained to simply imitate these experts.
So it learns, if you see think, generate like that expert, and if you see short, generate like this expert.
Pretty much. It learns that mapping, think means long, step by step. Short means short, direct answer.
That makes sense. It builds the foundation, the model learns the sort of syntax of the commands.
Right. It gives the model a diverse behavioral repertoire, as they put it, to draw from in the next stage.
Does this imitation hurt performance at all?
The paper mentions it can cause a slight dip compared to the original experts, which isn't surprising. But they found using more training data helps recover some of that. Diminishing returns, though.
Got it. So stage 1 is about teaching the model to obey the think or short command. Stage 2 is where it learns to give itself that command.
Exactly. Stage 2 is the core reinforcement learning phase. Here, the model is trained to choose the appropriate control token autonomously. And, crucially, to improve the accuracy of the responses it generates in both modes. It's learning to choose and learning to do better.
Tell us about the reward system they use for the RL. You said it balances accuracy and efficiency.
Yeah, it's designed to be simple but effective. If the model outputs short and the answer is correct, it gets a full reward of 1.0. Simple.
Okay, max reward for short and correct.
But if it outputs think, and the answer is also correct, it gets a slightly lower reward. 1.0 no minus a penalty factor called gamma. Gamma is just a small positive number, less than 1.
So a correct short answer is explicitly better, reward-wise, than a correct long answer.
Yes, exactly. The gamma term bakes in that preference for efficiency when possible. It nudges the model towards short if it thinks it can still get it right.
And what about wrong answers?
Harsh penalty, minus 1.0. Doesn't matter if it was short or long or which token it started with. Wrong is wrong.
Okay, so this system strongly encourages getting the answer right and using the shorter path when accuracy can be maintained. Seems logical.
It is. But applying standard reinforcement learning with this setup, well, they ran into problems.
What kind of problems?
They hit a big issue known as mode collapse.
Mode collapse. That sounds bad. What does that mean in this context?
It means the model's learning got stuck, really stuck. The part of the model deciding whether to use short or think stopped exploring both options. It would quickly just default to one mode, usually the short one, very early in training.
And just stay there.
Yeah, and essentially forget how to trigger the detailed thinking, even if it needed it later. The learning just collapsed onto one strategy.
Why? Why did standard methods like vanilla GRPO, as they call it, collapse like this?
This is where the paper makes a key technical point. It's really interesting.
Okay.
The issue boils down to a kind of signal-to-noise problem in the learning process, in the gradients.
Signal to noise. How?
Okay, think about it. When the model generates a long response after a think token, that response might be hundreds or even thousands of tokens long, right?
Right. Lots of tokens for the thinking process.
In standard RL, the learning signal, the gradient update from all those many response tokens, can effectively drown out the learning signal from the single control token at the very beginning.
Ah. So the one little instruction token gets lost in the noise from the huge output that follows it.
Precisely. The update to the part of the model that decides on the control token gets diluted, especially for those long sequences.
And because the think responses are much longer.
Exactly. Because the think responses are so much longer than the short ones, the think token's influence on learning gets disproportionately suppressed.
So the model basically learns, it's hard to learn from the think decision, so just stick with short.
Kinda, yeah. The model's policy quickly learns that trying think is hard to optimize because its signal is so weak, so it just defaults to short, where the feedback loop is shorter and clearer.
Okay, that's the clever part then, how they solved this mode collapse. That's the core contribution, maybe.
I think so, yeah. Their innovation is called Decoupled Group Relative Policy Optimization, DeGRPO.
Decoupled, meaning separated.
Yes. DeGRPO explicitly separates the learning signals. It's a modification of the standard GRPO algorithm.
How does it separate them?
Instead of treating the control token and all the response tokens the same way during the update, it handles them independently. It calculates the gradients for the control token policy and the response token generation separately, and then normalizes them independently.
Okay, so it makes sure the learning signal for the single control token, short or think, isn't overwhelmed.
Exactly. It ensures it isn't overwhelmed by the signal from generating the potentially very long response that follows.
So it gives the decision token its own dedicated attention during learning, like it scales its importance properly.
Essentially, yes.
Yeah.
They use a weighting factor, alpha, to balance how much the model focuses on updating the mode selection policy versus updating the response generation itself.
Alpha. Just the tuning knob.
Pretty much. By setting alpha appropriately, they found a small value like 11,000 worked well, they ensure the signal from the control token is scaled correctly. It gives it enough influence to learn an effective selection policy, regardless of how long the subsequent response turns out to be.
And what's the practical benefit of this DeGRPO decoupling? Why does it matter?
The benefit is stable training, plain and simple. It prevents that mode collapse we talked about.
So the model doesn't get stuck.
Right. It can simultaneously learn to produce accurate outputs in both modes and learn a nuanced policy for when to use which mode. It balances learning the how, generating good answers, and learning the when, choosing the right mode.
All right, let's talk results. Does this actually deliver on the promise? What did their experiments show? Did Thinkless with DeGRPO work?
They tested Thinkless on several math benchmarks. You know, the kind of problems that really require detailed reasoning, and the results were very positive.
Okay, give us the headline finding. What's the big news?
Finding number one, Thinkless dramatically reduces the need for that long step-by-step thinking, just like they hoped.
How dramatically?
On various data sets, it cut the usage of the think mode by anywhere from 50% to a massive 90%.
Wow, 50 to 90% less thinking.
Yeah, which leads to a huge jump in efficiency because it's generating far fewer tokens overall. Much faster, much cheaper.
Okay, but the million-dollar question. Does it sacrifice accuracy? That's the big trade-off here, isn't it?
Crucially, no. That's the second key finding. Even with this massive reduction in thinking, Thinkless maintains performance accuracy comparable to models that always use the long reasoning process.
Comparable. Even on tasks where thinking helps.
Yes, especially on tasks where thinking is genuinely beneficial. It doesn't just randomly skip thinking. It learns when it can afford to.
Can you give us a specific example from the paper, just to make it concrete?
Sure. On the Minerva algebra dataset, Thinkless chose the think mode for only about a quarter of the problems, something like 26%.
Only 26%. Okay.
That slashed the token count drastically compared to a model that thinks on every single problem. Yet its accuracy was virtually the same as the baseline reasoning model that always thinks.
Wow, so it's being very selective, very efficient. And on the really tough problems, the ones that absolutely do require thinking, does it still choose that mode? Or does it try to cut corners?
No, it seems to know better. The paper shows that on benchmarks known for being extremely difficult, like AIM,
AIM. Yeah, those are hard.
right? On AIM, Thinkless still opted for the think mode nearly 100% of the time.
Okay, that's important.
It proves it's adapting its strategy based on the true complexity of the task. It's not just defaulting to short, it's making a judgment call.
And I think you mentioned the RL also encourages shorter, long responses.
Yes, that was another interesting side effect. The RL process also seemed to encourage it to generate more concise reasoning chains, even when it did choose the think mode, making its thinking more efficient too.
So it's learning when to think and how to think more concisely when it does. That's pretty sophisticated.
Exactly. This adaptive behavior across different task difficulties is a significant advantage over those older methods, using fixed rules or separate routers, which might struggle to adapt.
Okay. You mentioned mode collapse and the U-shaped learning curve earlier when explaining DeGRPO. Did the results confirm that visually?
Yes, absolutely. Finding 2 in their results section visually showed how vanilla GRPO training quickly collapses to one mode, just like we discussed, usually short.
And finding 3.
Finding 3 explained that really cool U-shaped learning curve they observed with the successful DeGRPO training. It's a clear sign the learning is working as intended.
Explain that U-shape again, maybe in simpler terms. What does it show?
Okay, think of the letter U. At the start of training, left side of the U, the model is using the long think path more often.
Why?
Well, because it's warmed up on reasoning from stage 1. Right. And for harder problems, that long path is its best bet for getting the answer right early on before it's fully optimized the short path.
Makes sense. Start with what you know works okay.
Then, as DeGRPO training progresses, moving down the U, 2 things happen. First, the model gets better at generating accurate short answers thanks to the RL feedback.
Okay.
And second, gets better at identifying which problems it can solve accurately with a short answer and routing those specific problems to the short path. It learns to discriminate.
So it's learning which problems are actually easy enough for the quick win.
Yes. And as more problems get correctly routed to short, the rewards for the short path go up, naturally, and the model chooses it more often. That's the downward slope of the U-par. The proportion of think responses decreases.
And the upward slope on the right side.
That reflects the accuracy improving overall, but also a stabilization. Interestingly, the accuracy within the think mode might actually look like it drops slightly later in training.
Why would that happen?
Because only the truly hardest problems, where even detailed thinking doesn't guarantee a correct answer, are being sent down that path by the now smart policy. The easy and medium ones are handled by short.
Ah, so the average difficulty of problems tackled by think goes way up.
Exactly. So the U-shape visually confirms it's learning that sophisticated routing policy based on perceived difficulty and its own improving capabilities.
That U-shape is such a clear signal that it's learning to self-manage based on the complexity it perceives. Very cool. What about that alpha value in DeGRPO you mentioned? Did they explore that?
Yes. Finding 4 looked at alpha. Remember, alpha controls how strongly the model prioritizes learning the mode selection policy versus improving the accuracy of the generated responses.
Right, the balance between choosing and doing.
A higher alpha makes the mode selection update more significant, which can speed up how quickly the model shifts towards using the short mode more often.
So it affects how fast the model decides to stop thinking so much.
Right. But as the paper notes, you have to be careful. Too high in alpha can push the model to decide too quickly.
Like before it's ready.
Exactly. Perhaps assigning a problem to the short mode before the model is truly good enough to solve it accurately that way. It's about finding that balance during tuning to ensure the policy learns robustly alongside the generation capability.
And finding 5 just confirmed the effectiveness of the warm-up stage. That stage 1 was useful.
Yes, pretty much. It just validated that the initial distillation phase successfully prepared the model. It showed that these reasoning LLMs, after that warm-up, can indeed become effective learners for generating short responses and learning the policy for choosing them.
But they did mention refining that warm-up is an area for future work.
Yes, perhaps with more advanced distillation techniques or different setups. It worked, but maybe it could work even better.
They also included a case study on one of the data sets, right? To sort of illustrate the learned behavior.
They did. On Math 500, it provided a nice visualization of the learned policy in action.
And what did that show?
They plotted the probability the model assigned to choosing the think token for different problems within that data set.
Was it random?
Not at all. It showed a really well-calibrated curve. Simple arithmetic problems had a very low probability of triggering think.
As you'd hope.
Right. While multi-step complex problems that obviously require reasoning had a high probability of getting the think token.
So it visually confirmed that the model wasn't making random decisions. It was learning to associate query complexity with the need for deeper reasoning.
Exactly. It's compelling evidence that the learned policy is genuinely reflecting the difficulty of the task, or at least the model's perception of it.
Yeah.
It's learning a kind of self-awareness about when its brute force thinking is actually necessary.
Absolutely. It's moving from just a default behavior to a strategic choice. That feels like a step up in intelligence.
It does.
Of course, like any research, there are limitations. What did the authors highlight themselves?
Well, the main ones were related to that warm-up phase we mentioned. While effective, it was relatively simple, supervised fine-tuning, and could potentially be improved.
Okay. Anything else?
They also noted that their validation was primarily on mathematical tasks. Math is great for testing reasoning, but it's not everything. So future work should definitely expand this approach to a wider variety of domains and data sets. Text summarization, question answering on general knowledge, creative writing maybe to see how well this thinkless idea generalizes.
Makes sense. Test it beyond math. So bottom line, what's the big takeaway from the Thinkless framework in this paper, if you had to summarize it?
The main achievement is demonstrating a robust method powered by their decoupled GRPO algorithm that successfully teaches a powerful reasoning language model to autonomously decide when to use its detailed thinking process.
And the impact.
This leads to huge efficiency gains by avoiding unnecessary computation on simple tasks, all while maintaining performance on complex ones where you need the accuracy. It gets you the best of both worlds more often.
And the core technical insight that made it possible wasn't just RL, but that specific DeGRPO.
Yes. The insight is about handling the learning signals correctly during RL. You can't just throw standard reinforcement learning at this problem because the signal for the mode selection decision gets overwhelmed by the signal for generating the response itself, especially for long responses.
And DeGRPO fixes that imbalance.
DeGRPO solves this by ensuring that crucial decision signal gets the attention it needs to learn stably alongside the generation part. It's a subtle but critical adjustment to the learning algorithm.
Okay, this has been a fascinating deep dive into how AIs are learning to be smarter about how they think, not just what they think about.
It's a really neat direction.
And for you listening, imagine interacting with an AI that doesn't just blindly apply a heavy process for everything you ask.
Yeah, think about that experience.
It strategically chooses the best approach based on the complexity of your request and its own learned confidence. That could mean near instant, concise answers for quick questions you ask daily,
While still giving you the deep, detailed analysis for when you truly need it, for those complex problems, all potentially from the same underlying system.
That feels like a much more dynamic and useful interaction.
It definitely changes the user experience potential.
And it leaves us with a really interesting question to ponder, building on this idea. If large language models can learn something as subtle and strategic as when to engage their reasoning process, effectively learning to manage their own cognitive load,
Yeah.
what other forms of metacognitive control could they learn in the future? Could they learn how best to approach different kinds of problems? Could they learn when they need more information to be confident before answering?
Or even develop a sense of the limits of their own knowledge, knowing when not to answer.
Exactly. It feels like we're just scratching the surface of AIs learning to be truly strategic about how they deploy their intelligence. Something to think about.